And then where would you put that in?
So this is just right here,
Okay.
right? So I'm using the same formula.
Okay.
Here it's just, so my sigma is just d times the square root of n over 2.
Okay, but it's
It's just because I have unequal samples, my n is 14.4
okay.
because I have unequal samples.
Okay.
Do you see where we jumped in and you got that?
Yeah.
Okay.
Thank you.
Okay. Finally, my paired sample tests. Okay. Anytime you're going to go through and run power on your paired sample test, you need to go through and run the correlations across your repeated measures. The stronger the correlation across your repeated measures, the more powerful your test is going to be. If I go through and I measure people at time 1 and time 2, and my time 1 scores are completely unrelated to my time 2 scores, I've essentially run an independent sample test. Like, so my scores at time 1 tell me nothing about where someone's going to be at time 2. That's not going to happen. If it does, there's something really weird with your set. You should probably go through and take a look at things, right? But here what we're going to do is we're going to go through and we're going to take my effect size here specifically for power. We're going to calculate that as the difference in my mean, or difference in my mean at time 1 and time 2. I'm going to take that over this variance estimate, and I'm going to calculate this as my standard deviation times the square root of 2 times 1 minus the correlation between times 1 and time 1 and time 2. Okay. So again, remember when we went back through, when we were talking about effect sizes for a repeated measure sample, I'd given you sort of this as a formula that's sometimes used. This is where this is coming from. You see this same sort of effect sort of going down here. So this is a calculation that's related to power, but it doesn't translate into an effect size that's actually super meaningful, and it can make your effect size look way bigger than what it should in terms of something that's interpretable. So like, I would not encourage you to use this. It'll make your study look good, but it's actually pretty misleading in terms of like sort of what your actual effect is here. Okay. So again, let's go back through and think about this this Aronson study, and instead of imagining this as an independent sample analysis where we have the control group and the threat group separately, let's say that we go through and we have transitioned this into a repeated measures design. So we have a group of people, and we have them, so maybe say we randomize or counterbalance people, and first have them complete whatever task we have, either sort of with neutral instructions or under stereotype threat, and then have them do it again without the stereotype threat. Now this one will be a little bit difficult to sort of, because there's going to be carryover probably, but let's do this. Let's say we have everybody come in, just have them complete a task, neutral instructions, and then have them complete it again under stereotype threat instructions, and then go through and take a look. Okay, so we're saying that mean of time 1 is 9.6, time 2 7.55. I have 30 people total in this sample. My pooled standard deviation is 3.10. My test retest is 0.92. So very, very strong association between performance at time 1 and time 2, even though we're seeing a reduction. Okay? So with this information, what I will do is go through and take my standard deviation multiplied by the square root of 2 times 1 minus my correlation here, okay? And then if I go through, this is going to give me a value of 1.24, okay? Calculate my effect size as 9.64 minus 7.55 divided by 1.24. What do I get in terms of effect size here? Yeah. If I see a D of 1.69, that's massive, right? Massive, massive. But what happens if I just go through and calculate this like we probably normally would? So we got 9, or we go, calculate this as 7.55 minus 9.64 over and pooled standard deviation estimate 3.10. What's the effect size that sort of, like, I would argue is the more interpretable effect size here? Jenny, do you got it? No.
Sorry, I didn't divide by the right thing.
Yeah, I was like, nope,
Sorry.
that's.
I was just like,
You know what, I appreciate
I'll
your
take the
effort though,
numerator.
right? Yeah. Someone got it, any idea of it?
Negative 0.67.
Okay. And I'm just gonna go through in 0.67 because the sign is arbitrary on this, right? So if we go through, what I would say is, I would look at this and I would say that there appears to be a stereotype threat is associated, completing this task under stereotype threat is associated with about 2/3 of a standard deviation decrease in test performance, right? That's a very different thing than what we've got here, okay? I can't interpret this outside of it's a large effect, right? But it's not an effect that sort of translates into something meaningful, or I would argue represents kind of what's going on here. This is critical for calculating power, but not a good metric to report in terms of like quantifying your effect, because you've got this adjustment for the correlation between your measures, right? So something that from a computational standpoint is critical and necessary, but something I would strongly encourage you not to report, because it's going to give you a misleading estimate of sort of how big this effect is in practical terms, okay? And so something to be on the lookout when you're reading literature where people are using repeated measures designs and they're reporting effect sizes. I would really want to know how they went through and got those effect sizes, because it can be a huge difference, right? Basically, we've got over a full standard deviation increase in terms of this, like they're not comparable metrics. Okay. So, but if we go through and we do this, we got our effect size multiplied with the square root of 30, right? Again, this is just the same. This is just the same formula functionally that we use for our single sample test, because that's all a paired sample test is just a single sample test on different scores, right? And so what we end up is power equals 0.99, right? Above that, in fact. So we'd say, assuming the null hypothesis is false, the expected effect is expected to reach statistical significance 99% of the time given n equals 30, correlation or test retest of 0.92, and a population effect of 1.69. You'll see how we got those estimates there.
So if it's like inflated in this way because of the correlation, what do we do with this power value though?
Okay. So the power, so remember, and this is a great question, Anna, remember the power, we're calculating this power to determine how many people do I need to be able to claim evidence of an effect, right? So, and evidence for an effect in this case is to reject the null hypothesis, right? And so this is all kind of inconsequential. What this is saying is if I have 30 people in this design, I am hugely, massively powered, right? Like I am going to get a very, very, very small p-value, right? Now that doesn't say, this doesn't speak to anything in terms of like the actual metric of the effect and things like that. It just, if I were to, if this is the effect size, if these are the means of my two group in the population, if these are the means of my actual population, if the population difference under this sort of manipulation is exactly 9.64 minus 7.55, right? If that's what I'm looking for, and those assessments are correlated 9-2 with one another, over 90, like it's almost a certainty that every time I run this study, I'm going to be able to reject the null, right? And now I'm not going to get the same p-value every time. I just have to tip over into that test statistic where I get to just reject it, right? And so this is almost certain that I'm going to go through and find every single time, right? So the actual effect size, this is what we need this to appropriately calculate power. but it's not an effect size that's useful for like reporting as a literal metric for the effect that we're getting.
Okay, I see.
Good question. Other questions about this? Okay. What's going on with power in this example? Because before, in the last one, we went through and we had power of, so what is this? In the last one, so yeah, we're still doing stereotype threat. We got 9.64 minus 6.58. So what's the difference here? Tell me 9.65 minus, or 9.64 minus 6.58?
3.06.
Okay, so in this scenario, we've got a difference between my two groups of about 3 points, right? In the second scenario, again, we're saying the same stereotype threat thing, right? But what is the difference here, the change 7.55 minus 9.64?
Negative
2.08. Okay. So in the first scenario, we got a difference, an observed difference of 3. In the second scenario, we only have an observed difference of 2, but we have massively more power in this one relative to the previous one, despite having the same number of people overall. What happened with this one that made, like, threw our power through the roof? We have a smaller absolute difference, right? But our power shot way up. What happened? What do you think, Jenna?
It's something to do with the population.
Population variance, because they're not even standard. My variance estimates are still kind of the same. What changed across? What's the big thing that changed across this example and this example? What do we do differently? What are you gonna say, Lexi? Okay, so and the effect size changed a little, or it changed quite a bit because of what?
Is it the pooled standard deviation?
Okay, not the pooled standard deviation. What's our method here? What did we change from the previous example to this example in terms of our design? What's that?
The correlation.
Yeah, the correlation. And why do I have a correlation with this one?
Because the measurements are
Paired. There we go. Right. We changed this over to a repeated measure design. In the first example, it's an independent sample test. Our scores are uncorrelated because they're across different people. If they're correlated, that's actually problematic for the test, right? Here we switched over to a paired sample, right? And the sample size, total sample size was the same. The standard deviation estimate, here it's 3.1. Standard deviation estimate didn't change, right? So the total number of people didn't change, the standard deviation didn't change. The actual observed difference in scores actually got smaller with this, but here we're working with a paired sample, right? And because of that, the correlation here, our power shot through the roof, okay? And so again, thinking about the power of our repeated measures designs, okay? We can achieve far greater power with smaller differences than our between sample stuff, okay? So again, we're going through and using this corrected standard deviation in order to calculate this effect size estimate that doesn't have a ton of value in terms of just telling people what's going on, but what it does is it gives us the proper calculations for determining the power of our effects, or the power of our tests, okay? And this discrepancy is a function of assessment within individuals, right? I'm able to go through with my repeated measures stuff and parcel out all those individual differences, right? So if I look at Lexi's score compared with someone else's score, Hagen's score, they're different people, they approach things differently. There's so much individual different stuff that sort of starts to add static in the mix. But if I measure Lexi once, twice, 3 times, again and again and again, each one of those values are controlled by Lexi, because it's Lexi doing the same thing over and over. And what we get is we get less noise. We don't have to worry. We get start to partial out with these individual difference, stuff like that, by looking at that correlation. And so, again, the correction, the difference between my independent sample and my repeated measures sample is a function of this correlation across my repeated assessments, okay? My effect size and my power, my effect size estimate that I use for my power calculations and my corresponding power is going to increase as rho increases, and that rho is the correlation between your 2 measures. So has anybody done physiological sort of psychophys research before? Okay, Jenna has. So if I go through, Jenna, if I measure my heart rate or skin conductance right now, and my heart rate or skin conductance 5 minutes from now, what's the correlation between those 2 going to be? Super, super high, right? Because my heart rate, my skin conductance, there's only so much farther they can go, right? And so this is why the physiological stuff, we're looking at that in our repeated measures. You get correlations like 0.8, 0.98, 0.99 with one another, right? If I know my skin conductance right now, I can almost perfectly predict what it's going to be 10 minutes from now. And so we start to see changes in variability in that. It allows us to very carefully identify some very, very fine effects, right? Now, if I go through and I ask Lucas what his mood is today and what his mood is, 2 weeks from now, there's going to be less of a correlation. So you're going to have a little less powerful design, but still far more powerful than if I ask Lexi what her mood is today and Lucas what the mood is 2 weeks from now, and just kind of see what sort of just the environment of the world is having on mood, right? So again, another pitch for incorporating repeated measures assessments anywhere you can. There's some additional analytic complexity in sort of thinking about this, but it's just going to skyrocket your power, and it's going to make theses, dissertations, projects, things along those lines much, much, much easier to be able to go through and identify stuff. Now, we can't always do it. Sometimes the questions don't sort of, the things that we want to look at don't conform to a repeated measures analysis, but if they do, it's a really, really good way to increase the likelihood that you'll go through and detect the types of things you're looking for. Questions about any of this? All right. Power calculations with G-Power. Anybody use G-Power before? Okay. G-Power, really simple, free tool. Can go through and do some basic power calculations that are sort of good for a lot of applications. Sean and Ben really dislike G-Power. But it's a lot, because if you start to get into sort of more complex experimental designs, it doesn't account for the things that you need it to do. And so if you need to do those types of power calculations, G-Power is not the way to do it. But for just basic things, it's a nice tool. You can download it for free. It's a pretty slick thing for sort of just basic comparisons and things. So this is what the interface looks like. For a single sample test, let's say here, investigators are interested in testing the difference of extroversion scores in high school students relative to norms for university undergraduates. Previous research by Smith et al. I'm getting real creative with the names here. Provides estimates of self-reported extroversion in high school students on this measure: 65.3, standard deviation 13.5. Okay, so really easy with this interface. We're just going to go to your test family. You're going to find t-tests. You're going to find, for your statistical test, mean is going to be the difference from a constant. This is just a one sample case. Pull that from the pull down menu. Type of power analysis, we're going to look at a priori. Okay, we're compute required sample size given my alpha, my power, and my effect size. Okay, and then what I can do is go through and make sure that I'm looking at a two-tailed test. If I go through, and I can just enter my effect size in here if I want to, but I can also hit determine and go through and calculate it here. If you already have your effect size calculated, just type that in here. But if you want to, you can go through, hit determine effect size. Here's my reference value, here's my observed value, my standard deviation, and it's going to give me, and I hit calculate, and it'll give me an effect size of 3.55, say calculate, transfer the main limit, just kick it over there. Okay. So we've got my effect size,